So greetings to everyone. Uh, I will be presenting our paper on the cross-trigger energy Cepstral coefficients for Dysarthric severity level classification. So throughout the presentation, we will be first discussing about what is dysarthria and why severity level classification is required. Then what is the trigger energy operator, and followed by it, what is the cross-trigger energy operator. Then how the cross-trigger energy features are extracted, and what is the main property of the cross-trigger energy, that is the noise suppression, will be explained. We will be then discussing the experimental results, analysis followed by the analysis, and finally conclude the presentation. So first of all, what is dysarthria? As we all know that majority of the majority of the public can speak the intelligible words because there is proper coordination between the brain and the speech producing muscles. However, dysarthria is a neurological disorder which affects the human speech due to the discoordination between brain and the speech producing muscles. Hence, uh, this this causes the unintelligible words to be produced by the uh, patients. There are different types of dysarthria based on the impact and the area on the brain. So the treatment goes on. So the severity level of the dysarthria is determined by the speech language pathologist. Hence, the severity level classification is an important element for the speech language pathologist, as well as an important factor for assistive technologies like voice assistance or an ASR, maybe, and even the speech enhancements. So first of all, talking about the trigger energy operator. In the signal processing framework, trigger energy operator is known to track the instantaneous energy for the speech signal. In the continuous time domain, the trigger energy operator for any signal x of t is given by this equation. First derivative of the signal, the square, minus x of t into the double derivative of that signal, which is equals to the amplitude square into sine square of omega. However, in the discrete time signal, we can see that psi of x of n is equals to x square of n minus x of n plus 1 into x of n minus 1. Here, the TEO utilizes the single channel output, whereas the CTEO, that is the cross-trigger energy operator, which is an extension of the TEO, utilizes the multi-channel input for the feature extraction. Extending the TEO framework to the cross-trigger energy framework, we can say that psi of x of t with y of t is given by x dot derivative of the respective signals minus x of t into double derivative of the second signal. However, the cross-trigger energy is not commutative. Hence, we take the average out of the cross-trigger energy, which is expressed by psi of cross-trigger energy over the average x of n into y of n is equals to x of n into y of n minus 0.5 into x of n plus 1 into y of n minus 1 plus x of n minus 1 into y of n plus 1. This shows the functional block diagram of the CTECC extraction. We first take the input speech signal and apply it to the Gabor filter bank, which gives us the 40 subband filters. Each subband filter is operated for the trigger energy operator. Then we mean out the everyone and choose the minimum or maximum based upon the mean. and then we frame it and take the log and the DCT to obtain the CTECC feature. However, the main component of the CTECC minimum is the noise separation part. CTECC is found to suppress the additive noise, due to which it can capture the linguistic information properly in the speech signal. The experimental setup. For the experiments, we utilize the universal access speech corpus. Amongst the various speakers, we utilized on 8 speakers, 2 of each category, with particular number of samples. The trend test plate was given by 90% of the data was used for the training, and rest 10% of the data was utilized for the testing part. The classification accuracy was compared with the baseline STFT and various CTCC feature set. CTCC can be divided further into CTCC maximum and CTCC minimum. By maximum, we mean that we take the maximum. We take the maximum mean over the whole 40 subband filters, and in CTCC minimum, we take the minimum of the whole 4 subband filters. We see that CTCC minimum outperform the baseline STFT and CTCC maximum feature set with a classification accuracy of 95.76% on the CNN classifier. The performance evaluation for the various feature set was also statistically measured using F1 score, MCC, Jacquard's index, and the Hamming laws, where we see that CTCC minimum also outperforms the other all feature set. This is the confusion matrix for all the feature sets, where we see that CTCC minimum captures the true positives, maximum number of true positives compared to the STFT and CTCC maximum. Apart from this, we also analyze the latency period for CTCC maximum and CTCC for various CTCC features. Initially, we can see that for the lower time, we see that both the feature sets are performing equally good, but as it progresses further, CTCC minimum shows a greater curve or a higher classification accuracy compared to CTCC maximum features. This might due to the fact that CTCC maximum captures the environmental conditions, rather than CTCC minimum captures the linguistic information. Hence, to conclude this, we analyze the discriminative power of CTCC minimum in the Dysarthric severity, and CTCC minimum captures the better linguistic information, and in further, this can be utilized for the different data sets like Torgo, Numers, and home service corpus, as well as for various assistive technologies. Voice assistants also can be utilized as a further extension to this work. We will like to acknowledge the makers or the organizers of UA Speech Corpus, Ministry of Electronics and Information Technology India for sponsoring the NLTM project Bhashini, and consortium leaders Professor Hemay Murthy and Professor S. Umesh, and authorities of DICT. And these are some of the selected references. Thank you.
Thank you, Aastha. Any questions?
Yes, I have a question. Thank you. That was a very interesting talk. So your technique is halving the error from other techniques. So that's actually quite good. Do you have any intuition about the other half, the other 5% of error that you have? Do you have any idea? Is it possible to be better, or is it mislabeling in the data, or not enough accuracy in the data to be better? Do you have any idea of what you might be missing in the measure that you're doing to try to improve this further?
Sir, this can be further extended upon the larger data set. As you know that UA corpus is a quite large data set with multiple microphone channels and various kinds of speakers and words as well. We took a very small subsection for it, due to which we might have the 5% of error. If we cross check with a larger amount of data, we might reduce the error as well, sir.
Okay. Thank you.
Any other questions? I have a question. So have you compared with traditional MFCCs, or can you talk about how they are different from traditional MFCCs?
No, sir. Actually, we took the baseline as STFT only as well, and we haven't compared it with the MFCCs, but we will definitely try it comparing with the MFCC in future, sir.
Okay, yeah, I found it interesting because MFCC extraction follows a similar procedure, but they have Mel-shaped filters. They don't have subbands.
Right, sir. This might be due to the subbands capture the formant frequencies as well, sir. And linguistic information has formats are useful for structuring the speech and the words. So, so what is the effect on the formants, or how the structural are been structured in the mouth or in the speech might be better to capture.
Tanvina, you can go ahead with the question.
Okay, hi Aastha. Thanks for the presentation. I just have a doubt. You were saying the feature min is better than feature max, and you mentioned that max might be capturing noise, hence it is poor in performance. But then that is after applying Teager energy operator, and Teager energy operator already suppresses noise. So I'm a bit confused that even after doing TO, why does max capture noise and min does not capture noise?
I mean that the more linguistic informations have been captured by the minimum, CTCC minimum, or the rather than the maximum.
Okay, I mean noise at, I mean, what type of noise? I mean, that's the only question I have.
In the Dysarthric speech, it is found that there is production noise, sound production noise imposed by the speakers, which because of the unclear speech or something, or the distorted words. So that noise might be CTCC minimum might capture only the linguistic information and not the production noise.
Okay. And I don't know if you have time. Why is the latency different? Because I mean, why is the latency different? Because it's just min and max. So again, I was not bit sure that why is the latency different for min features and max features? Because it's, I mean, it's just a feature and you do min operation, max operation at the same time. I mean, I hope that is how it is working.
I'm not able to understand the question. Can you please repeat
Okay,
it?
maybe in the breakout rooms.
Yeah, okay.
We still have like around 4 minutes. So if you want to ask a question, I think the question was about the latency.
Yes.
Why the latency would be different?
Yeah, because I'm just assuming the operation is you have a feature vector, you do a min operation and a max operation. Or is there something else which I'm not able to understand? I mean, if it's
No,
just
no.
that operation, then
The feature that we have are different. For the minimum operation, we take the minimum of the all averaged out, and for the maximum, we take the maximum for all averaged out. So we have two different feature vectors. I would request the co-author Anand to elaborate this answer.
Okay,
if you could just go back to
so
the block diagram, I think I'll try to understand it from there.
actually, I
Yeah.
think so. The definition of latency we are trying to tell is like for how much small duration of speech utterance, how much accuracy we are getting actually. So here the for the like initial part, there is a 20 milliseconds audio itself or the speech signal. So for that, we are getting an accuracy of around
I
50.
see.
So
It's a
we
speech
are
sample
conveying that.
size.
Okay, yeah.
Okay.
We are going for the speech
Okay.
sample size. Right?
Okay.
So that's
Okay.
what we are presenting right now. Like
I
how
see.
much is the latency right
Ah.
now? Is that clear right now? Like or
Yeah. I mean, I mean, I was just the latency word was.
yeah.
Okay.
This is the
I
block
get it now.
diagram.
I get it now.
Oh, okay.
Okay.